Okay, one last little finishing touch that I want to put onto GLMs to generalized linear modeling. And that is this problem that we've been kind of avoiding conveniently of overdispersion. And so again, to remind ourselves, things like the binomial and the Poisson distribution have a single parameter that captures both the location and spread in one parameter. And so there's a theoretical expectation of what the variance should be around a binomial sample, and there's a theoretical expectation of what variance should be around a Poisson sample. But as it turns out in the real world, oftentimes we have more variance than our model assumes that there should be. And so this is the phenomenon that's called overdispersion, and it's a pretty common problem, especially with Poisson distributions. And so I just wanted to really briefly talk about an approach that one can take within the GLM framework with the function GLM, and then just really quickly introduce another distribution just so that you're aware of it. It's increasingly becoming a common distribution to use for Poisson type count data when you have problems of overdispersion. And so I'm just going to go through the little bit that we have in the notes that I've posted. And here you can see I cleverly said some quick thoughts on overdispersion. So again, that we know what overdispersion is then, and we know what the problem might look like, and we know how to diagnose the problem. So here I'll just read in some data, which I'm going to decide to don't need that, which I'm going to decide to model as a Poisson. And I'll go ahead and I'll make a linear model, a generalized linear model. And just as the example before, I'm just going to estimate the intercept. So all I really want to do is be able to estimate what that lambda parameter is. And we know what the point estimate is for that, because all we have to take is the mean. And that is our maximum likelihood estimate for the parameter lambda that these data were drawn from. But when it comes to statistical hypothesis testing, we also want to incorporate the uncertainty around that point estimate. And that's where overdispersion becomes a problem because, again, if your lambda is 2.4, there is a closed form solution of what you expect the uncertainty to be around that. And if our data are overdispersed, that means that we have more variation than the distribution is actually predicting, which means that when we're doing our hypothesis testing, that we are reducing, we are deflating the amount of uncertainty around our point estimate, which is going to increase our type 1 error rate, and it's basically just bad form because we're going to be making one assumption about a certain variance, and it actually could be larger. And so I'm going to go ahead and I'm going to run that. And then I will go ahead and I will look at the summary of this model. And here again, our first check that we want to look at is the deviance. And so here, the deviance, I'm seeing that it's a little bit bigger than the degrees of freedom. So maybe I want to check out and see what that looks like. And so I can go p chi-square 70.094 with 49 degrees of freedom. Lower tail equals false. So I do that and I get 0.025. And so that's the p-value for using that chi-square distribution, which means that if we stick with a threshold of 0.05, that means that our observed data are significantly different from our predicted data from the model. And that's not terribly satisfying because we would we'd like to be able to trust any hypothesis testing that we might do. So one solution to this are what are called quasi-distributions. And quasi-distributions were developed explicitly for this problem of overdispersion. And all that's happening in a quasi-distribution is that the computer is going to iteratively calculate what is a dispersion parameter that will serve as a multiplier so that we will increase the standard error around our point estimate of our parameter. And so you can see as the default when we use family Poisson that the dispersion parameter is taken to be 1. And that means that we know what the variance should be across the Poisson distribution, or for that Poisson distribution, and we should be able to model then effectively our data. But since we have this overdispersion problem, it's very clear that actually that probably isn't the case. And so we need to account for that. And we account for that by using what's called a quasi-distribution. And there's also a quasi-distribution for a binomial built into the GLM. But we'll go ahead and we'll use the one for a Poisson, and it's simply family equals quasi-Poisson. So I'll go ahead and I'll run that. And now I will look at what our output is. And so first you can see that we no longer have a dispersion parameter that is 1. Instead it's 1.19. And so that's going to serve as a corrector, if you will, a correction factor for the uncertainty around our standard error, or for around the variance around our parameter estimate. And so if we go back and we remind ourselves what, this is using just the Poisson distribution here, notice that this is our standard error, 0.09129. When we use the quasi-distribution, our standard error has now increased and it's 0.0996. Now granted, that's a pretty small difference, but it's still a difference. And if your data are highly overdispersed, which sometimes can happen in pretty dramatic fashion, you can end up with a very, very large dispersion parameter. And what that's going to allow you to do is to do honest hypothesis testing, because you're going to be accounting for that extra uncertainty around your parameters. And to demonstrate that that's all this dispersion parameter is I, here over here I've taken, that's the dispersion parameter, and then this is our standard error estimate from the overdispersed model, which again is our model based upon just a Poisson. So that's where that 0.09129 is from. So if I take that standard errors are in what? They are in units of standard deviations. Deviance is in units of variance. And so we'll take the square root of our dispersion parameter, and we'll multiply that by the standard error of the original Poisson model. And what we end up with, as you see here, is the same value. So basically that's what the computer is doing behind the scenes, is it's estimating the dispersion parameter, and then it's taking the standard error of the straight up Poisson model, and it's multiplying that standard error by the square root of the dispersion parameter, and that's giving us our new standard error. So our standard error has increased. Our standard error is increased, which means that we're less likely to commit a type 1 error, because now we're effectively modeling the uncertainty around our point estimate. And so that's in the general sense of how these quasi-distributions work. Note that our deviance has not changed, and that's because there is no closed form probability mass function for a quasi-Poisson distribution. Rather, we're fitting a Poisson to it, and then the computer is figuring out some penalty term, essentially, which is what the dispersion parameter is, which is why you will not get an AIC when you use a quasi-distribution, because there is no likelihood for the whole model. Now, if you dig deep enough and you're that interested in quasi-distributions, there are packages that estimate likelihood. They come up with a quasi-likelihood so that you could calculate a quasi-AIC if you're so keen on doing such a thing. I think that's a little bit, as I said, there could be a whole class just on generalized linear models, but this is a very common problem that people run into, so it was worth being familiar with it. The other solution, if you have overdispersion, is to pick a different sampling distribution. Again, all we've played with is binomial and Poisson, but there's a number of different distributions that we could potentially model our data as. And so one that I wanted to mention, because it's actually becoming increasingly more commonly used, especially when people are counting like reads, for example, of microbial data sets or whatever they might be, where you're actually counting the number of reads per microbe, and then you're trying to model that. So it is count, but very frequently that'll end up with an overdispersed distribution. And so the distribution is called a negative binomial, and it's it's similar. It's more similar to a Poisson. Actually, the Poisson is a special case of a negative binomial than it is to a binomial, which is maybe counterintuitive. But what the negative binomial is modeling, it is you set. Imagine that you have a binomial sampling procedure, and you have a particular probability, and we've already done this. So if you were to do, if you flip a coin 20 times, you have an expected number of heads or whatever it might be. How the negative binomial works is it is the expected number of successes until you get to a set number of failures. So maybe you're trying to estimate, how many heads will I get before I get 5 tails? And then as soon as I get 5 tails, I'm done, and all I'm doing is counting up the number of heads. It's used very frequently for things that have to do with rates as well. Without getting too much into the weeds, the probability mass function for a negative binomial, I just wanted to point out that the negative binomial does indeed exist, which is a nice thing. But we can set one up. Within the package mass, there is a function called GLMNB, which stands for Generalized Linear Model with a negative binomial error structure. And I'm going to take our exact same data as before, and I'm going to just go ahead and I'm going to run it into there. And then I'm going to look at the summary. And so here we have our estimates. We have a dispersion parameter. This dispersion parameter is actually just a parameter that this is the expectation that's within the probability mass function for a negative binomial, which means that we actually are now getting a likelihood. And as such, we would have an AIC, so we could, if we wanted to, we could compare various models. But what I want to point out is here, if we were to look at the residual deviance and see whether or not we're over dispersed, we can pop that in there, and then that would be the p-value. So we would accept the null hypothesis that our observed data is the same as our predicted data based upon the model. So there are these other distributions out there, and we're not going to do anything about a negative binomial in the class, and certainly won't be on the final or anything like that. I just wanted you to be aware that there are these other distributions that you could potentially use. Hopefully, you feel comfortable enough now with how to put together linear models, and you understand, at least conceptually, what's happening with link functions with generalized linear models, that if you get to that point, where you have your own data and you have overdispersion and you're concerned about it, you could either dive in on your own and think about what alternatives there might be for coming up with an appropriate distribution for the error structure. The quasi is always fine, and it's there, and people use that quite frequently. But more important, if you understand the language of how generalized linear models are working, and as long as you're kind of committed to making sure that you understand what those parameter estimates are going to be, that's where you could go in and talk to somebody, talk to a statistical consultant and ask the right questions, because that, you already have hopefully enough foundation where you can specifically ask the question. You can say, hey, I have this data, I tried to model it as a Poisson, I'm having all these overdispersion problems. Is there any other alternatives besides a quasi-distribution that is worth trying? If you ask a succinct question like that to a consultant, they're going to be very pleased, because usually what they probably get are people walking in with a bunch of numbers saying, analyze my data. But since we understand how those models are put together now, you can go in there and you can ask the appropriate questions and figure out how to solve that dispersion problem. So that's it. I just wanted to mention on how we're going to deal with, or how we might deal with, the problem of overdispersion. So yeah, that's generalized linear models. There's lots of, as I say in the bottom of that PDF, the 2 chapters on generalized linear models in that Michael Crawley R book are actually quite well written, and so we can always return to that if you want to explore a little bit more about these generalized linear models. So at that, I will say so long and good night.